Alright, okay, good morning, students. Okay, so my check first. Is the sound clear? Please raise your hand. Alright, okay, thank you. So, okay, little bit disappointed, Okay, attendance only 51, minus myself and the screen share, so less than 50 students. So anyway, expected Okay, actually, because less minus informed. So okay, and then I can see that most of you here actually basically is mostly it's from 5 students if I'm not wrong. Okay, so anyway, we start our class. So this morning we're going to focus on this chapter 6. Right, actually for Form 4 students, uh, this chapter is I haven't this yet, so that's why I use these 2 slots, okay, to cover so that we can finish the syllabus before open the school, right? Okay, so for the chapter 6, the first one, 6.1, diffractions of light, right, which is that experiments topics that we conducted today. So diffractions of light, okay, actually is the same as what you have learned in the chapter 5 before this for the wave phenomena. Okay, diffraction is one of the wave phenomena, okay, which is caused by the change of speed. Right. So if you're referring to a textbook here, textbook is saying it is given that this phenomena is occurred, right, when it's occurred due to the change in velocity of light. Okay. Actually, I not really preferring mention about this change in velocity. I preferring mention change in speed. Change in speed of light. Okay. Because when we mention the change in velocity, it have 2 meanings. Okay, as you know, the velocity is a vector quantity. So when we say the change in velocity, is either can be changed due to change in magnitude, or either it can be changed due to change in directions. So vector quantity consists of 2 information, magnitude and directions. So when we mention about change in velocity, so we don't know which one is changed. Okay. So, but once we say that it's change in speed, so it will be more clear. It's due to the change in magnitude. Okay. Because the speed is a scalar quantity, it doesn't involve the information about directions. So once you say the change in speed, so we know that it's become slower or become faster. Okay, when the light traveling through the medium in the different optical density. So when you mentions about the when you give explanations about these diffractions of light, the terms optical density is very important. You cannot just mention generally density, right? You cannot just mention generally density, just like the smart info given here. Last time in O level doesn't have this smart info, right? Which is very important for you to know why you must use the terms optical density. Okay, because optical density is not the same as a density which is defined as a mass per volume. Optical density is not defined. It's not defined as a mass per volume. Okay, mass volume is the normal mass density. Okay. So example, when talking about density of oil is lower. Density of oil is lower than the water. Okay, but the optical density of oil actually is higher than the optical density of water. So that's the reason why when we give the explanation, we always have to use the term optical density, because this one is referring to the properties of the light, how it behave when it entering the medium. Okay, so but anyway, when we conducted an experiment for the same medium, let's say we conducted experiment for the water with a different density. So example, when we add the salt or the any others can dissolve into the water to change the water density. So in that case, because we are studying on the different densities of water, so it's not the different medium, it's a different density of water. So in that case, density itself will affect, will affect the change in the speed for the these diffractions of light. If we will see that the relationship is directly proportional, means that inversely proportional, sorry, means that the denser the water, when we add more salt into the water, it will make the water denser. So in that case, the speed of light will be decreased. But we cannot compare this density from the different medium. Example, water, oil, glass, like this cannot. All right. So that is something a bit different lah. Okay. So that's why sometimes it was confusing why the experiment can be conducted by changing the densities of water or any liquid by adding the any other impurities into the medium to change its density. Why it will be make the result showing the density affect the speed straight away. Okay, but in the other side, we have to mention optical density. So sometimes you will confuse about this. So hopefully with the example I given just now, you clear about that. Okay, so these diffractions of light, is bending. Is bending of light due to the change in speed. So when you enter the optical denser medium, right? Optically denser, then it will speed will be decreased. All right, so this is how we study the incident angle and the diffractor angle as given in the diagram here. So, and these diffractions of light, you have to really clear, about the incident rate and the diffracted rate. Okay, whether it's from the optically denser to optically less dense or vice versa. All right. So based on these two diagram here, the first one, the figure 6.2, 6.3 is showing for the is from the optically less dense to the optically denser. So this one optically less dense to the optically denser medium. All right. So that was we made the angle become smaller because the speed of light decrease. Again, I don't really preferring using the velocity. I preferring using the term speed. Right, the speed of light decrease. Okay, and vice versa for the the light travel from the optically less dense toward optically denser toward the optically less dense medium. Right. Okay. So from the relationship between the incident angle and the diffracted angles as now, we can form the one's relationship to determine the one's value that we call diffractive index. Diffractive index actually used to determine the degree which is the light bends when the traveling from the vacuum towards a medium. All right. So which is very important with referring to a vacuum to a medium. Okay, actually not only vacuum also can be either the vacuum, either is A. Okay, it can be vacuum or it can be referring to from the A into that particular medium also can. Okay, and so because of the speed of light in vacuum and speed of light in A, actually there's no significant difference. There's no significant difference. So that's why we can referring either vacuum, either A also is fine. And as this speed of light, we divided by the speed of light in the medium, so it will be determine the diffractive index, which is give the symbol N. Okay, so from here you can see, just now is starting beginning using the term velocity, and when come to here suddenly use the term speed. So this is why one of the reason why from the beginning I don't preferring the textbook given the term velocity. All right, so that's one of the reason. Okay, so by right it's referring to the speed change in the magnitude itself. Okay, so this is one of the formula which is based on this ratio we can determine the diffractive index of the particular medium. So means if we have the two different medium others than the one of the medium is vacuum, so or the A example, let's say we have the two medium like this, which you have a medium X, medium Y. Okay, maybe example water and the glass. So in that case, you cannot apply this equation to determine either one's diffractive index. So later, when we discuss about the Snell's law, I will let you know why. Okay, so this is one the Snell's law. Okay, So the Snell's law, okay, it can determine different index for the any others medium when we conducted the experiments. Right. So here are the example between the two different medium, either water and the prospects, okay, water and the glass, okay, water and the diamonds. Right. So there are two different, the three different result here, all with the same incident angle from water, all with the same incident angle from the water, okay, which is 50 degree. So, but because of the different optical density of the medium that we have, which is a prospect, glass, and the diamonds, so all dissolve with a different diffracted angle. Okay, so from the conclusion that we can relate the relationship, all the informations, okay, to forming the for the this Snell's law, which is a n1 sine theta 1 equal to n2 sine theta 2. All right. So this is the formula that we have. Okay, according to this formula, we have the diffracting index medium 1, medium 2, and referring to the angle incident, okay, angle diffractions, theta 1, theta 2. So we deferring as a medium 1 as a incident, the source of the incident ray, okay, which is where the ray come from, and then the medium 2 is that the entering medium, right, from the medium 1 into the medium 2. So that's why they use the theta 1 as the angle of incident and the theta 2 as the angle of diffractions. So according to this, right, n1 sin theta 1 equal to n2 sin theta 2, when we take the medium 1 as a, as given the explanation here, when we take the medium 1 is as a, or either as vacuum also can, so the diffractive index will equal to 1, which is a smaller. So here actually quite important, very important, to let you understanding that, next one, remember, n is always more or equal to 1.00. It cannot be less than 1. It cannot be less than 1 for the diffractive index of any particular medium. So if you know about this, then you will notice that they experiment during the practical exam, your answer, which is the gradients of the graph, is presenting the diffractive index of the medium. So if you understand about this concept, you shouldn't give me the answer n less than 1. Right? Which is there are many students actually give me the n less than 1. So it's showing that your experiment conducted is wrong, or either the graph that you plot is wrong. Okay, so actually that day many of you plotting the wrong graph, because in your mind always the graph will be the responding variable against manipulators variable. But the problem is the day you experiment, your manipulators variable is the angle I. The responding variable is angle R. Nothing to do with the sin I and sin R. So when I ask you plot the graph sin I against sin R, right, it's not really follow always responding variable against this manipulators variable graph, because both sin I and the sin R both are calculated value, which is a secondary data. It's not the first-hand data from the experiment. So once it's a secondary data, the graph, it can be plotted in any way according to what we need to know from the graph. So because we need to use a graph to determine the diffractive index, so which is diffractive index is a sin I over sin R. So because of that, we plot graph sin I against sin R, so that the gradients of the graph straight away can present the diffractive index of the medium. Okay. So for this formula, okay, n1 sin theta 1 equal to n2 sin theta 2. So in the case, if we make the theta 1 as an angle I, theta 2 as an angle R, which is a diffracted angle, therefore we have the n1 sin I equal to n2 sin R. Right? And when we rearrange the equations, it will make it become n2 over N1, right? This one, bring it here, divided N2 over N1, and the R, bring it here, it becomes sin I over sin R. So, because of the defective index N1, right, which is in from the A or from the vacuum, so it's equal to 1. Therefore, any value divided 1 will be back to the value itself. So that's why we can simplify the equation as a defective index of any particular medium will equal to the sin I over sin R, which is the I is anchor from the A or vacuum, which is same as a beginning given here. This one. Okay, it meant back to this one already. So we can make it equal to the C over V, which is a speed of light in the vacuum or in the air over the speed of light in the medium. So it's equal to the defective index of that medium, right? So that is the conclusions when we simplify the equations from the Snell's law, right? Okay. So for the Snell's law, we have already remembered about this one. Once you apply this, it can be used to solve any questions, included the question like this, which is we have the two different medium, right? But if you want to use a conclusion simple equation, which is n equal to the sin I over sin R, or n equal to the C over V, this case you have to remember it must be from the A or vacuum. It cannot be any other two medium. It must be one of the medium enterings or which is the incidence must be from the A or vacuum. They only can apply that. Right? So hopefully that you understand about that. So this is an experiment that we conducted today, and then I do some modify because I don't really use a red box. Okay, so the related experiment video I already share with you in the group. Hopefully that you know what is your problems. Okay, actually today even for the Form 4 students, okay, quite numbers of them doing very well. Okay, actually I haven't covered this chapter yet, but the experiment I given is for this chapter, but they still can do because basically if you follow instruction you can do. Anyway, I already give you the guideline with the ligand and so on. So by right shouldn't have the problems lah. But so far there are quite numbers of students also, right? They do nothing, right? They just don't try to follow the procedure and conduct the experiment. There's, some of them they leave the whole paper blank, right? So I don't know why you just can't read and follow instruction and conduct the experiment, right? You as I mentioned before, you cannot expecting experiment given for your practical exam is an experiment that you have conducted before, or you cannot expecting that the experiment must be experiment either one in your textbook. I always told you experiment can be modified. Sometimes you can just do the really simple experiment, right? Which is not really related to any law, theory, or the concept that you study. It just want to really basics understanding to want to know about the relationship between any two quantity. So it can conduct the experiment so simple in that way only. All right. So the most important is read the instructions, follow instruction to conduct the experiment. Okay. Another problem is, uh, I don't know why, a few students, when they're recording the result, 20 degree, so you see here, there's no issue that you record 20 degree, 20 degree, 30 degree, 40, 50, and repeat the degree sign in the video. It's no issue. There's no issue. The issue is there are some students, I don't know why, when they write the degree, it becomes degree Celsius. Why degree become degree Celsius? They are different unit. You are not using thermometer to conduct experiment. you're using protector to measure the angle. All right. Okay. So I don't know why I have such a misunderstanding about this. Okay. Another one is from your protector, you only can read the smaller reading is 1 degree. You only can read, okay, 20, 21, 22, 23, and so on. But I don't know, maybe some student is AI robot, I don't know. They can read 21 point something like 20.56 degree. I don't know how they read. Okay. So after I check through, I noticed that this student, it seems like they plot the graph, they draw the line, and then reverse the reading. So it means that they're cheating. All right, so they reverse the reading to fill up the table. So that's why it have a 25.68 degree, which is practically you can't get the result. All right. So even if you want to try to cheat for the doing the exam, try to be smart a bit lah. All right. Okay. So okay. Okay, other than that two formula to determine the defective index of the any particular medium, we do have the other formula, which is ratio between the layer depth and the apparent depth, right? As showing the based on this slide again. Okay, so according to that experiment, so we can determine the defective index by the layer depth over the apparent depth, which is this one. Okay, capital H over the small h, also used to determine the defective index. Okay, and the experiment conduct, okay, basically is the similar that the experiment that I designed for you, which is we don't really use the red box. Okay, we just use the objects to see the image to the glass block, and then we can determine the angle. All right, so just like activity 6.2. Okay, so this is the one we also can conduct. And when we conducted the experiment, okay, so that this one I'm not sure whether they will be come out in exam or not, because it seemed like very high possibility lah for me. Okay, because the apparatus is very simple and easy to get for the all the school. Right, we just need the tall beaker, right, with the water and the pins, right, ruler, letter stand. So like this only we can conduct the experiments already. So this one, later open school, I think we already have 2 weeks time. Okay, after 2 weeks time, the lab cannot be used anymore. So your physics practical exam will be start on the 30th, okay, 30th January, right? So later when the school open, right? So the 1 week before it have to close the lab. But the problem is the week before is a Chinese New Year holiday. So we expecting the lab will be closed start on 16. All right. Start on 16 or start on 15. So it means that we only have 2 weeks time can use the lab. Right. So see how first I'll try to let you try for this experiment. Okay. Because it seems like uh the way how you study result will be more difficult compared to the way you study result with the align the pins. Align the pins, okay, actually is quite easy lah. So anyway, the experiment I will repeat again, okay, to let you understand about the concept and the phenomena that we conducted through the experiment. Okay, so this one, okay, you actually can try to do it at home, right? You can try to do it at home. So you just take any bottle or any bottom is transparent. Okay, the bottom is transparent. Even the bottom is not transparent also can, right? Is the bottom transparent better lah? Is when you have the bottom of the this glass or the any cups is transparent, then you just need a paper. On the paper you draw a line, and then you count, and then after that you put the glass on top of this line that you draw. Okay, make it touch on the edge here. So here is your glass. So and then fill out the water. So after that you can just use any pins, right? Or any pins or the pens also can. And then with the specific height of the water, the depth of the actual depth of the water, and then you just move the pens from the water up. Okay, and then when you see from top, view, right? On top view, when you see the line here, when you move the pens, right? The pen have to align with the line that you draw, and then after when from the top view you see actually they are not really aligned already. Even from the side view, you can see there's a line. Okay. Then after that you move your pen bottom up until you see the line with the pens or the pins outside is aligned. Then only you stop. Once you stop already, and then you have to slightly forward and backwards with position. You slightly backward here and then slightly forwards here to see. Slightly only, no exactly perpendicular on top. Okay, it's slightly move forward and move backward a bit. So it's still showing the line is aligned, then that position is correct. So this is what we call don't parallax method. Right? So make sure that slightly forward, backward also there's no any parallax error. Right? So they always align. Then the position is correct. So once position correct already, and then you mark the height. So you mark the height, so you measure from the bottom up. This one will be your this one will be the from the top. Okay, this one from the bottom. So you have to minus it because what we need to know is the apparent depth. Apparent depth means that it's measured from the surface down. It's measured from the surface down, not from the bottom up. Right? So that's why when we have to use the measure the bottom up, so you have to find the apparent depth by the h minus the y, because the y is the one that measure from the bottom up. Is that mentioned here? Measure the distance y between the pin I and the base of the beaker. So this one is means that here, when you stop here, this is the y. Okay, and then here is the hash, capital H. This one's apparent depth. So, but what we need to know is this. So that's why you need to know the apparent depth. It will be the capital H minus the Y. So as given here, this one. Because we need to know is the apparent depth from the surface down. So this is one of the questions usually they will design for SPM. Okay, so you have to remember when we're talking about the depth, so it means from the surface of the water down, not from the bottom up. All right, so have to take notes about this. Okay, so there's another formula we can use to determine the diffraction index. All right, so that's all for this 6.1. So next one will be the applications with the problem solving by the formula. So here's example 1 and 2. Okay, so now what I need you to do is try to solve the this formative practice 6.1. Do it now. I will come back after 10 minutes. So I give you 10 minutes to solve all these questions. For those already done before, so maybe you can do again as a divisions, right? So try to solve these two questions. So I will come back again now 9:35. So I give you 10 minutes. 10 minutes I think enough already. So later I'll come back 9:45. Okay. All right. Okay. So student, okay, are you still there? Please raise your hand. All right. So now we come back to this. Okay. Thank you. All right. So the question 1A, write an equations to delete the light that travels through the mediums. Okay. So in SPM, they definitely not going to ask you to write any equations lah, because all the equation formula are givens, right? But this kind of question will be very normal for your level after SPM, right? For your study after SPM, because there will be no any formula will be provided. Okay. So anyway, in this case, when you have to write an equation to delete the light that travels through the medium, so remember, you have to declare about the symbol that you use. Okay. And for the Form 5 exam today is still okay. But when I'm marking the Form 4 paper for the Form 4 students, there are some of them, when the question asks to compare, example, asked to compare the wavelength and the frequency, wavelength and the speed. So the student, I don't know why, okay, uh, the question itself doesn't give any symbol. So, but the student, when answer the question, is simply change the terms into the symbol. Example, when asked them to compare the wavelength, so they change the terms wavelength into the lambda symbol. Okay, so in the answer, it's just only lambda in the ligand 1.1. Example, ligand 1.1 is more than lambda ligand 1.2. So for the case, right, actually in exam, they can reject your answer because there is no any declare about the symbol. Even there are the standards, even they are the standard symbol, but you have to understand one thing. When the symbol is not given in the questions, when you write the symbol, you have to declare the symbol first. Right? When referring to the formula is all given the symbol, but in the instructions of the paper is already mentioned. The symbol in the questions, the symbol in the formula provided, right? The symbol itself is referring to the standards meanings presented by the symbol itself, right? Have a usual meanings presented the symbol itself. So it's the instruction of the paper is already clear about that. But when the moment you answer the question itself, you don't declare the symbol, so we don't accept actually. Right. So make sure when you use any symbol before that, you declare the symbol first. Right. So in this case, so we just repeat the formula just now, which is we have write the equation, which is we have write the n1, okay, since 75 degree equal to the n2 sin 55 degree. Right. So because it's equation, so you can write n1 sin theta 1 equal to n2 sin theta 2. And after that, you have to declare what is the n1, what is the theta 1, what is the n2, what is the theta 2. All right. So you have to declare. N1 is the diffraction index of the medium one. Theta 1 is a incident angle in the medium one. N2 diffraction index of the medium 2. Theta 2 is the diffracted angle in the medium 2. So you have to declare the symbol, right? Okay, and then after that, you can use that equation to determine the diffraction index of the medium 2 if the speed of light in the medium 1 is 3 times 10 power 8 meter per second. Right. So yeah, because this one is using speed of light, so in the case, so you can write here, okay, you also can write here as a n1 equal to c multiply c n2 multiply v. Also can like this, right? If you wish to change it, right? Okay, so here you will have the okay n2 over n1 equal to the c over v, right? Okay, what is the speed of light in the medium 2? So I think all this you can just use uh, the formula, okay, provided here. Okay, this one diffraction index of medium 2, right? So on Okay, so question B, hold on. What's wrong with question B? Determine the reflecting index of medium 2 if the speed of light in medium 1 3 times 10 power 8 meter per second. Nothing to do with the speed of light given. What? Question B is wrong. Question B is wrong. Right? Because this one is nothing to do to determine the reflecting index of medium 2. Because you are not given the speed of light in medium 2. So you want to determine the reflecting index of medium 2, you must use this anchor. You must use this anchor, substitute here, they only can get the reflecting index for the medium 2. Once you get the reflecting index of the medium 2 already, then only you can determine the speed of light in the medium 2. Okay, so given here, if the speed of light in the medium 1 3 times 10 power, this one by right it should be put it here. Right. But anyway, it gives you information here is to tell you this is the medium 1 and 1 is equal to 1.00. Right. It's want to give you these informations. Right. And 1 equal to the 1.00. So with that, then only you can determine the effectiveness of medium 2. Then after that, you're going to use it also for the determine the speed of light in the medium 2. All right. So, and then what is the apparent depth of the tank seen by the observer from the above the tank? Okay, so the tank is filled with oil with being height of 3 meters. The oil have the reflecting index 1.3x. Right. So means that this is a deer depth. Right. Okay, so when you apply 1.3x, so it will equal to the 3 over the apparent depth. So apparent depth will be the 3 over 1.3x. So definitely it will be less than 3 meter lah. So it's apparent depth. Okay, so this is a simple calculation. So I think the calculations with these two example, I think is enough already. So for me, next one, before I go to the next subtopics, I want to discuss about the drawing. So I really worry that the SPM it will ask about the drawing, even that is not the part of your learning objective. But since because of the light game all given the drawing, so I think it's better that you learn how to draw. Okay. So just an example regarding the okay. So let's say you fill out the waters here. Okay, here's the water. Then you have the objects at the bottom here. So where the eyes, let's say the eyes is here. So you're going to show how the eye able to see the object at this bottom. Because when we see, it will see to straight line. So when the light is not bending, definitely you can't see this object at the bottom here. You only can able to see this object at the bottom when you fill out the water because it will appear on the apparent depth. So in our drawing, we're going to show how you're able to see by the eyes when with the apparent with the virtual image, right? So what you need to do is you need a fixed point as a reference point on the object itself. So let's say I fix a point at the edge here as a reference point. So from this reference point, I draw a straight line. Okay, straight line from this point. Okay, toward the surface here. Toward the surface, and after that, when you get out from the water, it will be deflected away because the light is traveling from the optically denser into optically dense lens, so it will be deflected away normal. So it will bend into the eyes, okay, like this. Okay, so it will bend into the eyes. So here is how the light travel. This is how the light travel entering the eyes. Okay, but we see the image with a straight line. So it means that we need to extend this line. We need to extend this line. Okay, in the way like this. This is the line that we're going to extend, right? And then afterwards, what you need to do is you draw another vertically straight line upwards. Okay, so it will be like this. Okay, vertically straight line upwards. So where is the image? The image will be here. This one. This is the image that you see. So it will appear, okay, upwards by the intercept of the straight line for this bending diffracted ray meet with another vertical upwards straight line. So the intersection point here is the image forming. Right, so this is the image that you will see. Okay, and when from the measurement itself, so here that is your apparent depth, and this is your actual depth. Right, so in our drawing, we don't really care about the ratio, is this correct or not, right? We just want to see the concept. Okay, so if we want to referring to the actual, you have to make sure in the case here, apparent actual depth over the apparent depth must equal the refractive index of water. But in drawing, we don't really care about this lah. Okay, as long as you show that is a apparent depth and then the image appear in the shadow part. Okay, just like happens on the disc. So you see, when the positions of image driver from the viewing angle of the instructor. So instructor is the one to see. Okay, the where is the driver. So that's why we have to driver as objects here now. Okay, driver as an object. So that's why we have to draw the line, just like I showed you just now. You go here, okay, bend away, diffracted away with a bigger angle, and then after that, from the diffracted away line, then you continue straight line, and then the image will appear vertically upwards here. So just how I asked you to draw another vertical line, so that you know where is the positions of the image. Okay, so anyway, the image will appear vertically upwards. The image is not appear somewhere out of this borderline. Okay, it must appear vertically upwards. Okay, and then if based on the driver itself, okay, driver itself, now the instructor become the objects. So instructor become object. So for the instructor here, then you go into the water, so bend towards normal. Okay, and then after it goes straight line from the driver as the observer, so the eyes is here. So when we go straight line extend, so it will appear image vertically upwards here. So from here you can see there is the actual height above the water. Okay, but the apparent height actually is now small. Okay, because you are traveling, you are viewing the image. You viewing the image from the optically denser medium toward optically less than medium. So that's why the result will be inverted. Okay. So there is a drawing. You have to try to learn how to draw lah, as a step I teach you just now. Okay. So similar, same like this one also same. You can try to draw, okay, by this one. Even it's showing that the eye position is here, vertically upwards here. It's showing the eye position vertically upward. You still can draw like the method just now. You just need to get a fixed point. Let's say the center. You take a center as a reference point. So what you need to do is you draw an inclined line, okay, and then after diffracted away. So and then okay, and then this one and you extend it, so it will appear vertically here. So now based on this simple drawing, you cannot get the actual image in the light game unless you have to control. How to control? This one, the image is given already, right? So from this image, you draw straight line. From this image reference point. So from here you draw straight line. Right? So don't hit the beaker lah, don't hit the glass. So okay, and then draw like this. This one. Okay, like this one straight line. Use a ruler lah. Okay, and then from here, this one you continue, meet the point here R. So in this case, when you draw the normal, so you still get the, this one incident angle, here will be reflected angle, right? So regarding the problem, the question whether we really need to show this line or the line that we extend is not which is a virtual light. Do we really need to show this dotted line here in the drawing? Actually, it's not necessary lah. Huh? As long as you know the line is presented is what, then it's fine. Not necessarily must use the dotted line, because anyway in duality itself, the light ray, we don't really see the light ray traveling in straight line with errors and so on. So let's try whether you use a solid line or the dotted line, it doesn't matter. Okay. All right, so far that's all for the 6.1. Okay, is that any one of you have any specific question you want to ask or you need to clarify? If you have anything need to clarify, you can straight on your mic to ask. If not, then I will proceed to 6.2. Anyone's got anything need to clarify? If nothing to ask, we can proceed to 6.2. Please raise your hand. All right. Okay. Thank you. Okay. Total internal deflection. All right. So please be alert terms. Deflection. Just now what we learned is diffractions of light. Just now what we learned is diffractions of light. All right. So this is a 6.1, and now it's a total internal deflection. Okay. So the concept related. So when you answer, make sure you answer correctly, lah. Right. So don't mix up the terms itself. Okay. So the total internal diffractions, okay, is that only occurred. All right. Remember, it's only occurred when the light travel from a medium of a high optical density to the lower optical density. It means that it must be travel from the optically denser, from optically denser to optically less dense. Optically denser to optically less dense. This is must. Only that it can be occur total internal deflection. If you travel on the other way around, it can't occur the total internal diffractions, right? Okay, so here is an example when we're using the semicircular glass block, right? The semicircular glass block, okay, advantage is we can easily to measure the angle, not like using the rectangular glass block. Rectangular glass block, we cannot straight away measure the angle. We have to remove the glass block and then draw the line, extend the line. Then only you can measure the angle like the experiment that day, right? So by using the semicircular glass block, it's easier. Okay. So as you can see here, this one red box, the red box, our light is traveling from the A, enter the semicircular glass block. But why the case here consider as a light from the optically denser towards optically less dense? Okay, because here the light is travel straight line. So it means that from the normal line here, the angle that we have actually is the angle in the semicircular glass block. It's the angle in the semicircular glass block as an incident angle. So that's why this is considered as a light travel from the optically denser towards optically less dense here, which is now travel out from the glass block. Here is a medium, right? So from the glass towards the A. Okay. Then what happens here? What happens here? Okay. So what happens on the borderline before? Okay, before the light entering from the A into the glass block. That is why the reason we use a semicircular glass. Yeah. So come back to the concept that what we learned in 6.1 before. Let's say this is a borderline between the two medium. Okay, so let's say here is this is A, here is a glass. So when the light travel, okay, when the light travel from the A, right? After that, when you enter the glass, so it will bend towards normal. This is happens. Okay, because we need to show our normal line. So based on this normal line, here is our incident angle. This is our diffracted angle. Okay, so anyway, it will bend. But why, when we have the semicircular glass block, let's say example like this, we have a semicircular glass block. Okay, so here is our glass. Okay, so the question is why the light travel. Okay, so let's say okay, this one here is A. So why the light travel from the A into the glass block? It will be just go straight line without bending. Why is go straight line without bending? Okay, so what happens at this part? What happened at this part? Why is no bending like this? Why from the A into glass is bending, but this one from the A into glass is not bending? Why this is not bending? Okay, so you need to know where is the normal line. Okay, so when we show our normal line, the normal line be this one is a borderline here, just like this one. Here, this is our borderline between the two medium. So we need to show the normal line is here. This is our normal. Okay, here this is our normal line. Okay, which is perpendicular with the surface. And then now here is our borderline. Here is our borderline. So when we need to show the where's the normal line will be here. This is our normal line. So it means that our light actually traveling parallel with the normal line. Just like case like this. When you have the incident light ray travel parallelly with the normal line, it will be go straight forward. It will be go straight forward when is the incident ray is parallel with the normal line, which is our incident angle is equal to 0 degree. Okay, this one is the incident angle here. This is incident angle, angle I. So here angle I is not 0 degree, but this one when it parallel with the normal line, so it incident angle 0 degree. When the incident angle 0 degree, it will make the refracted angle also 0 degree. This is happens on the semicircular glass. It happens on the semicircular glass here. Okay, so as long as when you lead the light ray, towards the center, of the semicircular glass, so no matter where is the light from, right? Either it's traveling from here toward the center, either traveling from here toward the center, from here toward the center, from here toward the center. All this it will having a light parallel with the normal. All is parallel with the normal. All are parallel with the normal. as long as it's referring to the exactly center. Okay, so this happens on the semicircular glass, just like you learn in mathematics for the circle. When you have a circle, right, all the light pass through the center, all the light that pass through the center all the light that pass through the center, it will be always perpendicular. It will always perpendicular with the surface, like this one. No matter where you are from, right? As long as it pass through the center, so it will be always perpendicular with the surface here. Perpendicular, 90 degrees. So it means that as long as you have a semicircular or any curvature, where you have a line referring to the center of the curvature, referring to center of curvature, so the line it will be having the 90 degree with the surface. It means that you can get the normal line easily for any curved surface as long as it's referring straight line toward the center. So this straight line automatically is your normal line for the point, for the reference point. Right? So that's why when we use a semicircular glass, when we like lead the right ray toward the center, it will go straight forward. And after that, from here, before it came out from the glass block, this is our normal line. Because now our borderline is here. This is our reference model line now. Before this light came out from the glass block. Okay, so that's why we need to show our normal line here. It's a normal line. So mean this one will become the incident angle. Incident angle in the glass. So that's why it's showing the light traveling from the optically denser towards optically less length. When it come out to optically less length, it will be bent away. So we have the reflected angle is bigger. Okay. So in the case when we increase further our incident ray, like this. When we increase further the incident ray, so to have another bigger incident angle, here, this one, bigger than just now. So definitely it's going to deflector with a bigger angle, right? The R will be even bigger than before because when the I increase, R also increase. They need to obey this relationship, which is a sin I1 over the sin R2, sin R1 must equal to the sin I2 over the sin R2. Because the ratio is showing the ratio of the deflective index. Right, it must obey this ratio. So that's why I always have this result. Okay, so when I increase, R will be increased. So until the moment we increase I, until the moment the R come to the maximum. R maximum is the moment the R equal to 90 degree, which is this one is a maximum angle R, deflected angle 90 degree. So this moment here as given here, okay, as given here. So just like this one, when I increase the angle further, when I increase this angle I further, so it will make the R angle bigger. Alright, so angle R bigger until the moment the angle R equal 90 degree. So this incident angle in the optically denser medium, we call it critical angle. We call it critical angle. Alright, we call it critical angle. When the incident angle in the optically denser medium, the moments of the reflected angle is 90 degree. When the moment angle R is 90 degree, this incident angle we call it critical angle. We'll give a symbol C. We give it as a symbol C for critical angle. Why we call it critical angle? Because this is the angle either the light will be still deflected away in the A, or either when you bigger the critical angle, the light will be came in. So now when it came in, it becomes totally total internal diffraction. It's a totally refracted ray. Okay. The moment before the total internal diffractions occurred, somehow we always have this weak diffracted ray. Alright. So let's say this incident rate here, let's say incident rate here is 100%. 100% of the intensity. Okay, intensity of light is 100%. So when it deflected away to the A medium here, so let's say I just simply put let's say 90%. So the 10% actually is deflected. 10% actually deflected. So with the anchor here equal, this anchor R, this one is a deflected anchor. Here is a deflected anchor. They are using the same symbol, right? But they have to obey the diffractions phenomena, which is the anchor I equal to anchor R. So that's why you see these two actually is the same anchor. Okay, but due to the most of the light is diffracted away, right? If reflected away normal when the light is entering into the second medium, which is A less than optically less than medium. So that's why the portion that is diffracted inside here is only very weak. So which is intensity of light is very low. Okay. But once the moment you slowly increase further the angle I, okay, so this one will become stronger and stronger, which is the diffracted ray inside the glass itself. It will become stronger and stronger. So when the moment it come to the R equal 90 degree, it still have the diffracted ray at the borderline here, right? So means when you say that here's 100%, in this moment, maybe here this one is about maybe you can say that it's a 70%, right? That means that still have a 30% here. This one's just an example. Today you understand the concepts. It's not the reality. It doesn't work in that way. Right? The reality we have to do the calculation depends on the medium. Right? But this is beyond your syllabus lah. I just let you have a simple concept. Okay. So once the angle incident is more than critical angle, more the angle of incident more than critical angle, so it means that the R cannot increase further anymore. The R refracted angle 90 degree is the maximum here. This 90 degree actually is a max. Right? So when you have the I more than the critical angle, I more than C, so then now all coming already. That's why we call it totally deflected ray. So now 100%, 100%. So this one, that's why we call it total internal diffraction. Or now it's back to internal diffraction, is total. All right, there's no any portion outside. Okay, sorry. Okay, so this is for the total internal diffractions phenomena. All right. So the critical angle, I repeat many times already. Critical angle is the incident angle in the high optical density medium, when the angle of diffractions in the low optical density is 90 degree. Right, so the explanations of the critical angle in the definition itself actually not that easy because there are many keywords here. First, you have to understand critical angle actually is the incident angle. It's the angle of incident in optically denser medium. But incident angle in the optically denser medium, it can be many. But why there are specific angle we call critical angle? The specific of the incident angle that in the optically denser medium we call it critical angle is the moment when the angle of diffractions in the lower optically denser medium or in the lower optical density medium is equal to 90 degree. Right? So if we back to the formula that we learned in the 6.1 before this, okay, which is according to the Snell's law. According to the Snell's law, so we have the N1s, okay. I reverse it, okay. I reverse it so that I can divert it to the this ligand. We divert it, okay, divert it this ligand, okay. So let me erase all this first. Okay, referring to this ligand, so the graph is my first medium, A is my second medium. Then this one will be the theta 1, this one will be the theta 2. Okay. So according to the Snell's law, we have the N1 sin theta 1 equal to the N2 sin theta 2. Okay. So now this theta 2, theta 1, theta 1 is our critical angle now. So it means that N1 sin C equal to N2, theta 2 is 90 degree. So that's why we have this. When we rearrange these equations, so we will have what? We will have, okay, bring it out here. You will become N1 over N2 equal to the sin 90 degree over sin C. So it means that you bring it here and then you bring it here. So it's N1 over N2. Then the sin 90 degree over sin C. Alright? Okay. Because of the N2 is the medium A, N2 is a medium A, so which is N2 is equal to 1.00. And that's why here we have the sin 90 degree is equal to 1. So end up, this equation become equal to 1 over sin C. 1 over sin C. N equal to 1 over sin C. Okay? So this is how we determine the critical angle for the any specific medium, right? By deferring the other second medium is the A, right? This is how we determine the critical angle for the any specific medium by knowing on their defective index, right? So here is the one that I explained to you in this activity 6.4, all right? So how we get these equations? Actually, just a mathematics, all right? Okay. So from here, the one of the conclusion that we can make is the critical angle of the medium depends on the optical density of the medium. Critical angle depends on optical density of the medium. So the higher the defective index of the medium, the smaller the critical angle of the medium. Right? So means the denser the optical density of the medium, the smaller the critical angle. Right? Okay. So N higher, C smaller. Okay. N higher, C smaller. N higher, optical density higher. N higher, optical density higher. N higher, C smaller. Okay. So means that okay, I ask a question here. Right. So please respond the questions. Is optical density higher, medium, easier to occur total internal refractions? Please respond it. I repeat again. Is optical density higher, medium, easy to occur total internal diffractions? Please respond the questions. Is optical density higher, medium, easy to occur total internal diffractions? The answer is just yes or no. Is it the optical denser medium will be easier occur total internal diffractions? Girls, please respond the questions in the poll. Please go to the activity and respond the questions. All right. So only 19 watts. Now got 50 plus students inside here. Why only 19? About 21 watts only. All right. Okay. So I end the poll now. Okay. So seems like still has some of you not really understand the concept yet because the answer is not consistent. Okay. So with the total 32 watts, so I get the response 27 of you say yes, but the 5 of you say no. Okay. So now my question is I want to know whether the optical denser, okay, the the optical denser medium, is that easier to occur the total internal diffractions or not? Okay, so now let's say the question can be designed in this way. Within the exam, the question it can be just ask you very simple. Okay, let's say just like example like this. I give you a one medium, okay, which is diffractive index x. Diffractive index x equal to 1.62, right? Diffractive index y equal to 1.75. Okay, so which one will be easier to occur total internal diffraction? Right? Which one will be easier to occur total internal diffractions? With the given diffractive index x is 1.62, diffractive index y 1.75. So in this case, by understand the concept, you can easily answer. If you're still a bit confusing, you can try to get their critical angle first. Right. So why not you tell me the critical angle x and the critical angle for the y. So do the calculations now and tell me in the message. Okay, give me the answer. Critical angle for the x, critical angle for the y. So no one, please tell me how much is the critical angle for the x, how much is the critical angles for the y. Come on, I'm waiting your answer, girls. Please tell me how much is the critical angle for the x, critical angle for the y. No one want to respond. Okay, Vanessa, thank you. All right. Okay, so okay, thank you. So now, okay, critical angle for x 38.12 degree, then the y 34.85 degree. Okay, so okay, there is the answer for the critical angle. So now, how to understand about this critical angle? Okay, so now means here. Okay, let's say there is a borderline. Here got two borderline, and this is the medium x. Here's a medium y. This is a. Here is a. Okay. So okay, let's say yeah. Okay, now okay. Here is the incident angle. This is the incident angle. Okay. So let's say here both incident angle here. Okay, let's say here 30 degree. 30 degree. Okay. So 30 degree, 30 degree in the case. All right. So what happens for this medium x? So I give you the three answers to choose here. First one, or maybe four answer. 1, 2, 3. 3, 4. Okay, here. So for the medium X, answer A, B, C, D. Answer A, B, C, D for the medium X. Right? So for the medium X, answer is B. Right? So for medium X, answer is B, correct. Okay. So how about the medium Y? So same, A, B, C, and D. Okay. So for medium Y, A, B, C, D. A, B, C, D, which one? For the medium Y. Right? So the answer still the same, B. Answer still the same, B. Because both 30-degree, okay? Because of both 30-degree, this one, the 30-degree, both incident angle 30-degree is less than critical angle. Both 30-degree is still less than critical angle. When less than critical angle, so the light will be diffracted. The light will be diffracted. So that's why we choose answer B. Okay, we choose answer B. Okay, so now next. Okay, so I repeat again, the ligand. Same as just now, I have the medium X, medium Y. Here is A. This is A. So now I increase the angle now. Okay, so now I make all the angle here now. This one's 35. 35 degree. 35 degree. Okay. A, B, C, D. Okay, so remember just now we already determined based on the diffractive index given, we already know that each medium X and Y, they are critical angle. So now I want to know, okay, for this ligand X here, which is now this ligand, compared to this ligand. All right, so now I make as a questions lah. So here is question 3, question 4. Okay, so question 3, what is your answer? question 3, what is your answer now? Okay, question 3, what is your answer? All right. So question 3, the answer is still B. The answer is still B, right? It doesn't it doesn't have any difference compared to the question they asked before this. All right. How about the questions 4 now? Question 4. So now the question 4 is the answer is D. All right. So from here you can see what happened on the question 4. The medium Y with the incident angle 35 degree, the total internal diffractions is occurred. Means based on the same incident angle 35, the medium Y, which is a higher diffractive index, which is the optically denser medium, or we say that optical density medium is higher with a smaller critical angle, it will make it easily occur total internal diffractions. So when this 35 degree, Y is already total internal diffractions. But the X haven't yet. Because the X 35 degree incident angle is still less than critical angle. So the light, it will be still diffracted here. The light, it will be still diffracted. Right? It's still diffracted. Means we didn't get the total internal diffraction yet. We do have the diffractor ray, but it's a weak diffractor, weak diffracted ray, right? But this one, we have the total internal diffractions already. Means there is no any diffracted ray anymore here. No any diffracted ray. 100% in, 100% back. Just like acting like the mirror now. Right? The borderline acting like the mirror now. Just like for the beginning, the textbook give you this picture. The surface of the water acting like the mirror to reflect the image of the total. Okay, so there's a concept about total internal diffractions. Okay, so remember, optically denser medium with a higher diffractive index, it will have a small critical angle, means it's easier to occur total internal diffractions. Okay, so why we need the total internal diffractions? Okay, just like example, diffractive index of the diamonds, 2.42. So with the critical angle of the diamond is 24.4 degree. So that's why with this 24.4 degree, when we cutting the diamond into the particular shape, all right. So that's why the diamond always have the particular shape, is to ensure. So the diamond shape, right? Okay. So the diamond itself, cutting of the diamonds. All right. So the diamond, why always the given the shape is like this, is a diamond shape. Okay. Because when the moment the light entering the diamonds, right? So it will bend towards normal. When bend towards normal, when you go to the other angle, actually, this one's like it's not so good. So you entering here, okay, bending. So when you come to this part, right, this angle actually is more than it will make it more than 24.4 degree. Is it 24.4? 24.4. Okay, so actually it's more than 24.4. Okay, this data is more than 24.4. So it means that it doesn't deflected away. So it will be happens here. Total internal deflections. So total internal deflection. And then we count this angle, the total internal deflection occurred again. So count to this, total internal deflection occurred again. So it means that it will be internal deflect few times until the certain moment only it came out. So that's why the diamond always look like have the sparking inside the diamond because of the this total internal deflections. Okay. Then for with the higher diffraction index showing the diamond have the high optical density. Right. So and then in the case, usually the case for the solid medium, when you have the high optical density for the solid medium, it will be usually have the higher density also. That's why the diamond is a higher density. Okay. So this is also how we differentiate between the real diamond and the fake glass diamond. So nowadays the people can easily make the fake glass diamond. So how we check? One of the checking is based on the diffractive index. Right, so they will check the sparking. So when you compare the real diamond and the fake diamond, actually the sparking will be obviously different. Right. So the fake diamond, the sparking is not that much compared to the real diamond. Right. The one without using the any devices to check, just only observed by our eyes lah. Okay. So but if you want to really know whether there is a real diamond or the fake diamond, the one of the really simple way is without sending to the shop, you just take any hammer and then you hit it. If it doesn't broken, then the one's a real. It's broken, then it's a fake diamond. So this one very easy to check. All right. Okay. So but anyway, the regarding the sparking will be different. Okay. So that is uh, about the concept related to total internal deflections. Okay. So and the natural phenomena application of total internal deflection in our daily life. Okay. So in this is photograph 6.2, due to total internal deflection, you see that is here the beautiful or the decorative lamp show in the like 6.2. So here this is one. Okay. So all this is actually a total internal deflections. Okay. And this is one of the very simple example. Okay, how we bending the laser light. Okay, so we bending laser light when we make the hole here. So by right, this laser light will be just penetrate through straight line, penetrate through straight line. Okay, forward because the light is not bending. Okay, so but when we open make a small hole, when open, so we notice that this laser light it will be follow the water. All right, because of total internal deflections. Here is the water. So when the laser light hitting here, so this angle is more than critical angle. So it will be total internal deflections, of course, so it will be bent inside, or deflected inside. And when we come to this angle again, so it will be deflect. This one will be more than critical angle also, it will be bent where will be total internal deflections occur. So that's why it will be follow, and then at the end it will fall. It will fall according to the falling of water. Right, this is happens just like our fiber optic. Okay, and here the formations of the rainbow is one of the natural phenomena. Okay, when the sky have the water drops. Okay, when the sky have a lot of the water droplets, right? So you're able to see the rainbow. But to make sure to see the rainbow, you have to always uh, make sure the sun is behind you. When the sun is behind you, right? So you can simply see the rainbow. right in front of your eyes, right? Because of the total internal diffractions. Okay. So another one phenomena that related to total internal diffraction is mirage. Okay. So the mirage, usually we only can see it through the way it's a hot day. During the hot day and the hot and bright day, so only we can see this mirage. Okay, so just like example, when you see the straight routes, right, the right in front for far away, not really far lah, so sometimes it's very close. Okay, you can see the route just like have the floating water, or there's a floating image. Actually, that's what you see is a mirage, right? When you go there, actually there's no water there, or there is nothing there actually. Right? All what you see from the far away, the image appear above the root, look like the water, pool water. Actually, it's not the pool water. Okay, actually just a image, virtual image, which is we call it mirage. Right? Just due to the total internal diffractions occurred from the layer to layer. Okay, just like example here, for the hot air, it's less dense. Okay, cool air is denser. So it means that the light is travel. Let's say the light to deflect the image of cloud into our eyes. So the incident ray is from the denser towards less than medium. So that's why it always deflected away normal until the moment this anchor, right? This anchor is more than the critical anchor. So the total internal deflections occur. That's why it will be bent upwards. So it will bring the light from the far away enter our eyes. Okay, so and then we see the image go straight line. So that's why it becomes a virtual image appear here. Right. So that is mirage due to the total internal diffractions occurred. Another one we can use it to design our prism periscope. Okay, actually the periscope we can use a mirror, right? Instead use of the prism, we can use mirror to design the periscope. When you use a mirror, will be like this lah, really simple. Right, you just put the mirror here, 45-degree mirror, 45-degree mirror. Okay, so that when the light enter, it will deflect 90 degrees downwards due to the incident angle 45, 45. Okay, it's also same, 45-degree, 45-degree. So this is using of the mirror. Okay, compared to the prism, we put the glass prism here. So glass prism is based on the total internal diffractions phenomena. So it will forming the image which is will be clearer because the brightness will be higher compared using of the mirror. Okay, this is 100% total internal diffraction. So 100% in, 100% out. So intensity of light will be higher compared to the mirror. Mirror is something like this. Okay, so here when we design a prism with a mirror, right? Periscope, so periscope with a mirror. So this is our mirror. Mirror have the thickness. Mirror actually is a layer of glass. Layer of glass. The behind here have the layer to deflect the light. So this is what happens when you see the light is deflected here, right? When light deflected based on the 45-degree arrangements, 45-degree arrangements. So this is make your incident angle 45, deflected angle also 45. Okay, but the problem is actually the part of the light is already entering this glass, right? By the reflected towards normal, it's entering the glass. So this is make the intensity of light deflected will be less. So means that it come in 100%. So after deflected, it will be less than 100% intensity. So this is why if when you compare to with the prism will make we will be produce a clearer image compared by using the mirror, right? Because the mirror have a less intensity of light will be decreased when after it deflected due to the part of the light actually entering the glass to make the mirror. Okay. Sorry for the noise. Ayo. Okay, actually currently I'm at hometown, so in my brother house. So my brother house basically quite similar like in the childcare center because he have twins and the baby less than 2 years old, right? So every day is okay. I enjoying with the noise from the baby. Okay. Okay, the next one, the optical fiber, as I told you just now, just like the similar explanations happens on the these fallings of light, okay, for the this activity 6.6. Okay, only the difference is the design of the optical fiber. The design of the optical fiber here, we have the inner cord and the coating. Okay, it means that we have the two layer. Actually, we have the two-layer glass. Right. So this two-layer glass is to ensure that our total internal diffractions will be more easier to be occurred to ensure there's no any signal can be penetrate out accidentally due to the suddenly there's a certain changing when we bending the optical fiber in the certain angle actually will become see you see this one in the certain angle the angle will become small, so to ensure there's no any possibility for the signal can be penetrate out from the inner cord, so that's why the design we must be have the inner cord and the outer cladding to ensure the total internal diffractions is always occurred. That's why the signal will be in from one end and come out on the other end. Right, so that's the design of the optical fiber. Okay, used in the telecommunications for our high speed internet lah, right? And this cat eye diffractor, so also based on the total internal diffractions concept. So and then I designed the questions for the Form 4 final year exams already. So hopefully you understand now about this total internal diffractions. Not the Form 4, it's a Form 5 trial exam. Okay, Form 5 trial exam. Okay, so and then here are the example for the problem solving with the calculation involved. N equal to 1 over sin C, right? So actually, uh, this is a substitution of formulas only. But today there's a one teacher asking about one question. I think this one the question 2. Okay, try to do this question 2. Tell me what's the answer. I think question 1 determine the angle, defective index, right? So this one question 1 quite easy lah. Okay, do a question 2 for me. Determine the critical angle of the optical fiber. All right. Okay. So now the question need to determine the critical angle of the optical fiber. All right. So okay. So that's the solutions one. Solution one. We use this one. N equal to 1 over sin C. Right. So that's C will equal, let's see, 1 over 1.8. Solution 2. Okay. We if we apply the Snell's law, then it will be 1.8 0 sin C equal to 1.40 sin 90. So means 1 0.80 over 1.40 equal to the sin 90 degree over sin C. So means C will equal to the shift sin 1.40 over 1.80. Okay, so now please walk. Okay, which one? S1 or S2? Okay, please respond, girls. I only see that 23 volts. How about the others? Right, 29 watts only. So now I stop now. Right, so most of you still you go through the solutions as one, right? Okay. So regarding these questions, okay, determines the okay, determine the critical angle of the optical fibers here. Okay, so from what we learned before this, okay, you see that this formula. Okay, when look at the example 2, if the diffraction index of the optical fiber is 1.51, determine the radius of the anchor x. So in this case, okay, we apply the Snell's law, N1 and N2 here. So N1 is differing from the A, all right, into the N2, okay, for the this to determine the anchor x here. This one by the using the uh, to find the diffracted anchor. Okay, this is not the total internal diffractions, right? Okay, so when we're referring to the original critical angle formula, okay, we conclude that it can be determined by n equal to the 1 over sin c. As long as we knowing about diffractive index, right, then it will be straight away use the diffractive index to determine the critical angle. So when we have the outer cladding here, whether it can change the diffractive critical angles or not, actually is not ready. So, but the day when we discuss about these questions, actually we don't really further discuss about the detail for this case. All right. Okay. At first, I preferring this answer. At first, I preferring the solution 2. Okay, but after they consider against, if we preferring the S2, it seems like critical angle of the particular medium, it can be easily changed. Right. So the concept is seems like incorrect. By right, according to that n equal to 1 over sin c, the critical angle of the particular medium, it shouldn't be changed. Just like the diamond critical angle 24.4 degree is fixed already. The water is fixed already. Okay, so by right, when you want to know about the critical angle of this optical fiber, right? If this optical fiber we are referring to this inner cord only, it should be this one. But when this optical fiber is differing to the whole optical fiber, then the calculation will be different already. The calculation will be come to the S2. Okay, calculation will come to the S2. So for me, the question actually is not really clear about actually what they're differing. Because if back to the question itself, okay, it just only asks you to determine critical of the optical fiber. It doesn't specifically mention whether we want to know about the inner core or actually includes the higher diffraction index surrounded by the cladding material. All right. Okay. With the lower diffraction index. Okay. So end up, what is the actual the critical angle of the optical fiber here? So we need to clarify about this. So for me, this is not the good questions. Okay. This is not the good questions. Okay. But according to this result, you see, with the this angle, it shows you the critical angle of the this angle. They say that this one is a critical angle. Based on here, this is a 90 degree. So it means there is a critical angle. So in the case, we have to apply the Snell's law, which is with the N1 sin theta 1 equal to the N2 sin theta 2. By right, according to ligand, it shows there's a critical angle. So it means that we are not referring to the diffraction index of the inner core only. We are referring to the ratio of the inner core and the outer cladding. So it should be 1.8 sin C equal to 1.4 sin 90 degree. It should be like this. Right? So, but the problem is if we're using this one, you will notice that this C is about, I'm not sure whether we calculate or not. I think the C is, this C I think is about 51.06 degree if I'm not wrong. Okay. And if we're using the other one, solutions one, which is C equal to the 16 1 over 1.8. So how much is this one? 1 over 1.8 is 33.75 degree. So, which is this one will be the smaller, easily to be occur the total internal diffraction. But when it comes to this one, it seems like not that easy, right? So, okay, how to understand the design? Why the design like this? It will make this critical angle become bigger, which is not easily to be occur total internal diffraction. By right, it should be this one, which is more easier. Okay, so actually like this. The inner core itself, the critical angle is 33.75. So let's say it's happened, we have the angle less than 33.75. So let's say we happens here in the certain bending. So suddenly the angle here is only 32 degrees, let's say, or 33 degrees. 33 degrees, which is less than critical angle. So what happens on this angle? The theta 2. Okay, so now we try to calculate when the here is 33 degree, which is less than critical angle of the inner core, 33.75. So it will be diffracted to the outer cladding. Then how much is the angle here? So now you try to calculate. So you see 1.8 sin 33 equal to 1.4 sin theta. Okay, so the theta will equal to, you can do calculations also. So now the 33 sin multiply 1.8 divided by 1.5, then the sin answer, so it will be 44.45 degree. So mean 44.45 degree. Right, so this theta 2 will be 44.45 degree. 44.45 degree. So come to the other side here, also 44.45 degree. Okay, and then what happened to this 44.45 degree? So outer cladding 1.4. Okay, 1.4 means that 1 over 1.4 16, right? So the critical angle the critical angle for this outer cladding, the C is equal to 45.58 degree. Okay, so with this example, okay, compared to without the outer cladding, there will be no chances. Okay, there will be no chances for the light to bending come back in. Okay, let's say here is without outer cladding. Without outer cladding means that here will be the 1.0. Means it will be straight away go out to the A. Go out to the A. So will be 1.8 33 since multiply so if without the outer cladding, okay, so let me explain to you like this one. Yeah. Okay. So compare to the okay. So here there is the outer cladding here. So which is we have the inner chord n equal to 1.80. Then we have the outer cladding n equal to 1.4. Okay. So comparing to this one, only have the inner chord 1.80. Outer chord is the A 1.00. This is straight away go into the A without the outer cladding. Okay. So compared to these two cases, when I have the incident angle 33 degree, both 33 degree. Okay. So which is just now we already know the critical angle for the n equal to 1.8. N equal to 1.8. The critical angle is 33.75. 33.75. Okay. So n equal to 1.4. C is 45.58 degree. Okay. So anyway, the critical angle of the n equal 1.4 actually is not important for us. Not important for us. Okay. Okay. We just want to know what happens if without the outer cladding compared to with the outer cladding, what happens. Okay. In this case, the angle deflected away here, the angle out here, compared to this angle deflected away here, the angle out here. So now we want to know the R1, R2, what happens with and without outer cladding. Okay. So R1, okay, R1 will equal to the 1.8. Sorry. R1 equal to the sin 1.8 sin 33 over 1.4. Okay, R2 without the outer cladding will be equal to the sin, right? 1.8 sin 33 over 1.00. Okay, so the case here is multiply 1.8 divided 1.4. This one you will have the deflected angle 44.45 degree. And if without the outer cladding, the R angle will be 78.62 degree. So means without outer cladding here, with the incident angle 33, there is a possibility to let the signal deflected back with the total internal deflection will be not possible because the angle deflected 78 degree. There's no possible for the signal come back in because we have no any other medium. We straight away go out to the A already. But for the with the outer cladding here, even there's a incident angle 33 degree, but because outer cladding is a still considered as optically denser compared to the A layer here, we still have the chances. We still have the chances on the certain angle, the signal will come back in. Because we still have another layer outer cladding towards the A. Still have the chances for the angle to come back in. And then it will reflected with a smaller angle, 44.45. Okay, so because the critical angle is 45.58 for the outer cladding, it still have the chances for the light to be come back in. Because I just only simply give you any angle 33 degree. Okay, slightly more than 33 degree, still less than 33.75, then will be possible for the light to come back in. That's why we need the outer cladding. Okay, but for the only the inner core without outer cladding, there's no way for the light after it reflected away out from the inner core, then you will straight away not possible to come back in anymore. So the signal will be lost. Okay, once you bend the optical fiber into a certain angle. Okay, so anyway, for answer these questions, if we referring to ligand, it should be solution 2. Okay, it should be solution 2. For me, the question will be better if asked determine the critical angle of the inner core without showing the ligand. Then they will be better for the questions. But once with the ligand given like this is labeled already critical angle of the optical fiber, so the answer it should be referring to the solution 2, not the solution 1. Because optical fiber talking about the overall. Right? Okay. So but anyway, this part is beyond your syllabus for me. So I still haven't go and find the detail yet. Because understanding about the design of the optical fiber, right, in the reality actually is not that easy as the formula that we learned on it. Inventors about the optical fiber, actually by one of the professor from Japan, if I'm not wrong. You can try to search up. And then the inventors, the physicist invented this optical fiber. He won the Nobel Prize few years ago, right? Because of these inventions of this optical fiber, it changed our human telecommunication history. Without optical fiber, we don't have the high-speed internet that we can use for today, and further increase to the internet 5G. Because of that, okay, so that they give this Nobel Prize to this science, this physicists, those invented this optical fiber. But right, the books have to give this information about this optical fiber, but it doesn't have. So anyway, hopefully that's exam it will make it clearer when they design the questions all right, hopefully okay. So that's all about the total internal diffractions, right? And then regarding the question B here, what's the advantage of the fine optical fiber? Actually, it's already given here, right? Why must a material optical fiber be the high optical priority? Okay, so there's a high optical priority will be allowed the critical angle along the fiber optic to be consistent. All signal enter the fiber will be experience the total internal diffractions, right? So that's the answer you can use to answer it. All right. Okay. So also here, make of the glass inner core and other layer. Right. So the signal can be sent repeatedly without disturbance from the electrical signals. Okay. That is a design of the fine optical fiber. All right, so that's all about the total internal diffractions. So I will continue a little bit for this 6.3 image formations by the lenses. Okay, so image formation by lenses actually that is the extent from the 6.1. This extent from the 6.1 because it's about the diffractions phenomena, diffractions of light. This is a convex lens. This actually is a glass. So when the light enter into the optically denser medium, it will be diffracted. But due to the glass design has a curve shift, so the changes of angle, it will be bending in the different way. So we hold on, sir. Let me ask the children, the kids, shut up first. Okay, thank you. Okay, so we have the convex lens and the concave lens. Okay, all the terms here, optical center, principal axis, axis of the lens, focal point, object distance, image distance, focal length. Their explanations all given here already, so I don't want to repeat all about this. So you need to read and try to understand it. So I will straight away discuss how you're going to form the image by the drawing that I get. Hello, Jing Jing. Jing Jing. Okay, so for the Form 4 students, okay, you need to learn about the characteristic of the image. We have the real image, we have the virtual image, okay, we have the upright, inverted, okay, and magnify, diminish, okay, same size. All these are the characteristics of the image formed by the convex and concave lenses. Okay, so when you look at this convex lens here, focal point convex lens is the rear. Why we call it rear? Okay, and the focal point of the concave lens is virtual. Why we call it virtual? Okay, when you look at this like that. So this lens you can consider just like the example understanding about the glass. So it means that the light will be enter and penetrate through it. Okay, so that's why when the light penetrate out from the lens, so because of the curve shift, all will be converged to a point. This point we call it focus point. And this focal point we call it real focus point because of what? There is a light hit on this point. So it means when you put a screen here, there will be the light hit on the screen. So this is what we call real light. Then the focus point, we call it real focus point because the light is hit on the screen, hit on the paper, right? So, but for the concave lens, okay, when the light pass through the lens, it will be diverge. It will diverge, spread out. Diverge from a point, when extend, it will form a point here. Diverge from this point, we call it virtual focus. Because this is the light that unable to projector on the screen, right? You cannot put a screen here to get the light projector here. Because when you put a screen here, it's blocking. By right, the light orb will be penetrate through the lens, so the screen will be behind here. But the problem is the focus is the one extend. We extend the line here, then the focus is here. So that's why we call it virtual point or the virtual focus. So when talking about the virtual image, means that the image we still can see the image. Only the difference is the image doesn't projector on the screen. It just appear in the space. Okay, it cannot appear on the screen itself. Just like when you stand right in front of the mirror, you see your image inside the mirror, not on the mirror surface. It's inside the mirror. You can see the space. You don't tell me when you stand in front of the mirror, your face is appear at the surface of the mirror. If you say so, means that your image appear on the surface of the mirror. When you try to move forward towards the mirror, then the image on the surface it will be moved towards you also. Then it will come out from the mirrors already. Then it will become the ghost story already. Right? So actually you still can see there's a space inside. That's why the image appear inside the mirror. We call it virtual image. Just because the image we cannot let it projected on any surface. At school, LCD projector projected the screen image on the screen. That one we call it real image because there is a light hit on the screen, projected the image on the screen. Right. So that is how we understand about the real and virtual. Okay. So that's why for the convex lens we call it converging lens because it converts the light to a point. And then the concave lens, we call it diverging lens because it diverges light from a point, okay, before the lens, right? So that is how we understand about the converging and diverging lens, and also the meanings of the real and virtual. Okay. So for this part, the most importantly to learn is first you must learn how to draw the ray diagram for the formations of image. Okay, we have the three different ray. We have the three different ray as given in the diagrams here. The ray used in the drawing of the ray diagram for the convex lens and the concave lens is slightly different. You need to know which focal point that you use, right? So there is the one that the students are always a bit confusing. You see, here we use this focus. After that, we use this focus. And this one, we use this focus. After that, we use this focus. So that is why it make always make the student confused. Okay. So for me, very easy. All right. You just need to learn either two out of the three light ray here. You no need to learn all the three. All right. We only use either two. Okay. As long as these two, it can meet the intersection is the way we form the image. Okay. So and please do not try to memorize this table. Don't try to memorize this table by the different object positions. What happens to the characteristic of the image? Do not try to memorize this. Right? Don't wasting your time to memorize object infinitive, the characteristic image, the real inverted image, blah 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 blah. Please, don't wasting your time. Okay. Anyway, there's a one correction I want to make here. This is wrong. When object at F, right, you cannot determine the characteristic of the image. Because of what? Image is forming at infinity. When the image forming at infinity, we don't know the image is whether it's a real or virtual, upright or inverted. Right? For sure, it's magnified up. But we don't know whether it's a real or virtual. Because the image infinity here, infinity here. It can be real, it can be virtual. We don't know. Right? Because once the object more than f, all the image is real. When the object more than f, all the image is real. Less than f is virtual. So when at f, it's borderline. Either real or either virtual, we don't know. What we know is image form infinitive. But when you're checking the overseas syllabus, IGCSE, if I'm not wrong, it's only mentioned there's no image form. Because we can't form the image. Due to that, the light ray is parallel. When the light ray is parallel, there's no intersection, you cannot form the image. Alright. So it's parallel either on the positive side, either on the negative side. So okay, and this part I already discussed with Mr. Chia, which is the head of the writer of this textbook. So he's agreed with my comments, and then we were also referring to the few university reference book. Finally, he admit that there is a mistake of his team. So actually, in his reference book that he's published, so it's already made the corrections. But the textbook, only the correction can be made after we have the second versions. But second version usually they only will be published after 5 years, right? Because the textbook expecting to use at least 5 years, 5 batch students they only can change. So that's why what I can tell you is this one, please erase it. All right, this one's wrong. Right? Okay. Okay, and then about the formation of the concave lens also, you no need to memorize lah. Okay, what you need to learn is how to form the image. Okay, so okay, first we always need a principal axis. Principal axis, okay, one horizontal line, principal axis. Okay, and then afterward we need a lens positions. So we need a one vertical line. Okay, usually for the drawing formations or image, either with the mirror or either with the lens. Okay, usually we will ask the student use the graph paper, because graph paper it will be easier for you to control the distance. Okay, because graph paper you have the grid line, it's already show you all the length. Okay, so you can referring the how many division, one big division is a 2 centimeter, okay, and so on. You can easily check the distance and the length. Okay, but if you draw on the normal foolscap paper, you need to use the ruler to measure the length, right? Okay. So anyway, you need the principal axis and the one vertical axis as a position of the lens. So this position of the lens, when we want to show the symbol, what lens you use, okay, you don't need to draw too big. It's just a symbol presented that is a convex lens, the symbol there's a concave lens. So let's say when you want to show there's a symbol of the convex lens, you can show like this convex lens, just a small size, enough already, right? Okay, you want to draw it bigger, up to you lah. Okay, but sometimes the ligand, you don't want to disturb the drawing because our student draw big or small, right? So sometimes the ligand will just show like this. Then it's showing about this is a convex lens. Okay, so this is a convex. If there's a concave, they will show like this. So when there's a concave lens, it will show like this, right? Okay, so I think the textbook it doesn't give this one. Yeah, the textbook doesn't give that one, right? So the textbook still using the lens. So to let you understand the light entering the lens, right? If you want to show also can. Okay, you just show the lens. Okay, example like this. Okay, so all right, so now we focus on the convex lens. Convex lens. So first you need to fix your focus point. Okay, you need to first fix your focus point. So left and right hand side here. So use your ruler lah. Make sure the same. Okay, make sure the focus length is the same from the optical center here. Optic center. Okay, this optical center. Optic center here. Oh, okay. So and then after that we need to get another one here, 2F. 2F. Right? So means all these distance are the same. All the distance here should be the same when you measure. Right? It should be the same. Okay. So that's why you need to use a graph paper, is better. Okay. Right. So after that we need the object. So object, it can be here. There's one object here. It can be here. Right. So it can be here. It can be here. Or it can be here. Right. So you have the difference object distance. Okay. No matter where is object distance, always remember the first one that you draw, it must be from the top of the object toward the optic center and go straight. It's the first one you're going to draw. Alright, this is the first one you draw. So I draw a few all together, right? This is always the first one you draw. So by using the different colors, hopefully you can differentiate it, right? I all combine it together. So this is the first one that you draw, first line. From the top of the object toward the optic center and go straight, pass through. It's the first line. Okay. Second line, so now, first again, yellow colors one. Second line, make sure it's parallel with the principal axis. Parallel with the principal axis. So it means it's horizontal line. So means no matter where is the positions, as long as all the object is the same height, so all these are the same. All these are the same. So all these will be the same lah. So when I draw one by one, it will overlapping because all are using the same height of the objects, right? So it will be all the same parallel. So you see all will be overlapping. Okay, so it become like this. Okay. Then after that, the next one. After parallel until the position, which is a vertical line, position of the lens. So we're going to let it bending because enter the lens, okay, optical tensor, it will bend. So where it will bend towards the focus point. So it will reflected towards normal. And now the first one here, deflected towards focus. Right? Or we convert to the focus point, then we extend it. Okay, yellow with the yellow, yellow refer to the yellow. And then the orange, also same. Here it will deflect to focus. So deflect to focus. Basically, you see all, it will be the same lah. All will be the same. Okay. So and then the next one, the red color. Deflect to focus, all is the same. Okay. All will be the same. And then the next one, okay, purpose is still the same because referring to the same focus point. Okay. And then the last one, the blue, also the same. Okay. So now I'm going to reverse it to let you see one by one where is the image. Okay. So the yellow colors one, we're referring to yellow colors. Okay, which is this one. I change this one as a, okay, here the yellow colors, here the yellow color object. So now yellow color they meet here. So it means I have the image here. This is my yellow image, which is referring to this yellow object. And then the orange color, so here's orange color. Right, I need to extend this line here to the F, extend the line until you meet the orange color. So you meet orange colors here. You meet orange color here. So this is my orange color image. Okay, and then continue for the red color. So red color will be here. So extend until meet the red colors here, intersections here. So it means my red colors here. So getting bigger, right? Okay, so this is for the red colors objects and the image. Okay, so the next one, the purple color. Purple colors. Okay, purple colors. Now this F referring to F, then go straight. So it cannot meet. It cannot meet because of what? They are parallel. They are parallel. It cannot meet. Even extend backward here also cannot meet. Here. You extend backward here. Extend backward here is also cannot meet. That's why at infinitive. At infinitive. Right? So there is no image. And then the last one, the blue color. Oh. Sorry. Okay. The third word is begin. Right. Okay. So the F, go to F. So from here you can see the blue colors. We're referring to blue colors. Right? It getting split apart. So definitely it cannot meet after here. So, but before that, it seems like I have a possibility for them to meet if I extend it. So that's why I extend it. And then this line also I extend it. Then now they meet here. So here's the image. They meet here. Then there's the image forming here. For this blue color. Okay. So now, what you can study here is all these are real. Real, real, real. All these are real. For this object distance, which is a symbol U, object distance more than F. Object distance more than F, all the images are real. And all the real images are inverted. All the real images are inverted. This is pairing. Real must inverted. Means the upside down. The image appear upside down. Right? We call it inverted. Okay. For the object distance, less than F. Object distance less than F. So our image is virtual. Virtual. Right? Object image is virtual. Right? So the image is virtual and upright. Right? Virtual upright. Okay. So that is the pairing. This is pairing. Virtual always pair with upright. Real always pair with inverted. Then the size, based on drawing, you can determine the size. So from here, the first one, which is the object far away from the 2F, means the object more than 2F, right? Object more than 2F. So you have the smaller size, diminished. For the object equal to 2F, object distance equal to 2F, so you have the same size actually. When you draw with the graph paper, you can see it's obviously same size. So for the object, okay, distance less than 2F, more than F, in between F and 2F, so it's magnified. It's magnified. When the object at F, infinity. Object equal to F, image infinity. It cannot be determined. There's no image form. Alright? So this is how we combine all the ligand together by learning how to draw. With the 2 line, enough for us to complete the ligand to get the image already. You don't need to draw until the 3rd line. Right? So that is a basic way how you learn to form the image. Yeah. And then you can try continue with okay, now we continue with the concave lens. So concave lens is slightly different. Okay, because we need to know concave lens, we are not using this F. Convex lens, we use the F here. Okay, the F after the lens. Okay, because convex lens we have the real F. Remember, convex lens we have the real F. Concave lens we have the virtual F. So there's a different story. So for the concave lens, so same principal axis, and the one vertical axis presented the positions of the lens. Alright, so here is a concave lens, right? So, or we sometimes we use a symbol like this. Okay, same like just now, we need the F. Okay. Okay, so here we're using the virtual F, remember virtual F. So on the sides, on the object side, okay, because the light by right from here, it penetrates through, then this one will be the real. Here, if you appeal here, will be the virtual. Because the screen should be here. The screen should be here, so the light hit on the screen, projected on the screen, there's a real. But we cannot put a screen on the left hand side here, so because the light will be blocking, cannot pass through the lens. Right, so anyway, when you appeal here, will be on the left hand side will be the virtual. So there's a concept about the real and virtual. Okay, hopefully that you understand. So the concave lens, we have the virtual focus, so that we're going to use this virtual focus. Okay, and we have another 2F also. So why I need this? Because I need to show you all here. Okay, no matter where is the positions of the objects. All right, so let's say more than F here. Okay, sorry. And then okay, I duplicate it. So let's say I have another here on the 2F, another here on between. Okay, another here on the F, another here less than F. So same like just now. Remember the first line always towards the optic center. Always towards the optic center from the top of the object towards the optic center here. Go straight. Okay, always referring to this one. Remember about this optic center here. This one, optic center. Okay, cool. Right, okay, so the next one, orange color from here, go through optic center here, go straight. Okay. And red colors also from here toward optic center. This is always the first line. Always the first line. Okay, the next one on the F, purple colors, always from here. Okay, purple colors. Okay, so the last one, the blue colors, okay, from here to optic center. Okay, so this is the first line, exactly like the line. Okay, so now the next one is, okay, from the top of the object, parallel with the principal axis. Now I use the white colors. Parallel with the principal axis. Remember just now I told you parallel with the principal axis here, right? Until hit the lens. So now we're referring to F. Just now because of convex lens, we're referring to F here. But now we're referring to this F, virtual F. So, but it still have to penetrate through. Then it means that it will be deflected away like this. So it means that it will be go through this like that. Okay. So according to this, you see, all is the same, no matter where is the positions of the objects. When you draw the second line, all is the same. No matter using the yellow color, orange color, red color, purple color, or blue color, it will be still the same because it will be parallel with the principal axis. Parallel with the principal axis, we see this one, parallel with the principal axis. And then afterward, hit the lens and referring to the F here. So, and then it will be deflected away. Or be diverged. Diverged from the focus point. All is the same. So now you can see, now we can form the image already. So let's say we're referring this white color as a yellow colors. So as a yellow colors. So it means that when it hits and then referring to F here, so deflected away. Which one's the diverged? So it means that it will meet here. This is our first image form. Yellow color image here. Right? Yellow color image. And the second orange color image, orange color object here, orange color image will be here. Okay, and then the next one, the red colors. So here's the red colors. And then the purple colors. Okay. Purple colors. Okay, so image will be here. Purple color will be here. Okay, and then the blue colors will be here. So for the case concave image, no matter where is your object, our image always will be the same, which is all the image you can see. The image always is a virtual plus upright, and it will be smaller, or we call it diminished, compared to the objects. Okay, so that's why it gives you only two light game, and always the same: virtual, upright, diminished. Regardless you're on the F or not, more than F, less than F, it will be the same. So this is happen when you all combine in the one light game. So this is how we draw for these formations of the image by the lenses. Okay, so this is a focus on this 6.3. Just only the drawing, which is according to the title here, image formations. So we need to learn how to form the image by the drawing. Okay, and then for drawing itself, you need to learn. You need to learn how to give the characteristic of the image form. Okay, so and then the next one about the linear magnifications. All this we discuss tomorrow, lah. Right. So today we finish here, and then there's a little bit more to finish the 6.3, and then we straight away continue for the 6.4 and so on to finish our chapter 6 by tomorrow. Right. Okay, so thanks for joining the class. Okay, so that's all for this morning. Okay. All right, so you can left now unless you have a question to ask. If not, that's all for today. Thank you.
Thank you, teacher.
Thank you, teacher.
All right, bye.